Welcome to this decarbonization showcase hosted by NYSERDA's Empire Building Challenge. Its purpose is to familiarize you with technologies and strategies to facilitate decarbonizing our building stock. All sessions will be recorded and posted to the EBC Showcase Series website. Each presentation will be 20 minutes, followed by 10 minutes in which the presenter will respond to your questions, which you can post in the webinar chat. And now it is my pleasure to introduce Lalit Chordia of Clean Heat Technologies.
Thank you, Saul. Hi, everybody. Good afternoon. I'm Lalit Chordia, CEO and President of Clean Heat Technologies. As the slide says, we are a spin-off of Thar Energy. Thar Energy has been in business of providing heating, cooling systems and power generation using CO2 as the working fluid, both as a refrigerant in the heat pump systems and also the been building supercritical systems or CO2 systems for the last 35 years. CO2 is a great used worldwide, nutraceutical, pharmaceutical, and electronic industries. We build these systems in Pittsburgh. We are a US company. We build it locally here and we ship it all over, providing full customer support service for installation and servicing. Today, my content is about converting concepts that we have had under Thar Energy into reality, and the about heating and cooling. On the heating cooling, simultaneously, hot air,
Lalit, your audio is breaking up a little bit. If you're using a mic, if you can try just speaking directly into it, that might help.
Okay, sorry. Wait a second. Can you hear me now?
Yes, coming in loud and clear. Thanks.
So just to repeat, our focus today is on heating and cooling technologies, both simultaneously and also producing hot water or steam, which is the high temperature process heat or high temperature heat for heating buildings. So that's the focus of today's conversation. And what I want to show you here is we were one of the 7 finalists for NYSERDA for the Empire Technology Prize. And this is the photograph of where we were in New York almost a year ago, we are talking about. And we are one of the few companies, if not the only company, who's trying to produce steam using CO2 as the working fluid. So CO2-based heat pump for the production of steam. Now, why CO2? CO2 is a natural refrigerant. And with this heat pump concept that we have, we can produce steam with or without cooling. In other words, simultaneous heating and cooling. And we can do hot water also, again, with or without cooling. Now, our products will be a drop-in replacement for gas-fired boilers. And we always look from a cost point of view, what is the right size base load that we need? And we can use additional existing boilers to provide above the base load. And before I go to the base load, let me just talk to you about why CO2. Now, the advantages of CO2 is that first it meets or exceeds the A1 requirements. It's safe, non-toxic, non-flammable, and non-corrosive. We use CO2 for extraction of food products, so that means the FDA has approved it, the EPA has approved it, so it's a very, very nice fluid to use. As a matter of fact, after water, CO2 is the best natural fluid that's out there. It is very inexpensive. A kilogram cost you maybe 20 or 25 cents, while a kilogram of a refrigerant, modern refrigerants, will cost you over $500. And from a maintenance cost, it's easy to maintain because you do not need a certified technician to maintain it. If you go and maintain a heat pump and you have to vent out the CO2, no issues at all from an EPA, OSHA point of view. You don't need to collect the refrigerant. You just charge it with a new refrigerant. It does not affect the ozone layer, so it has the least impact on global warming, and it has a large carbon footprint reductions. And most importantly, it's unaffected by any future legislations or taxation because it's a natural fluid. Now, why we like CO2 besides the environment side is that if you look at the size of the tube, which you see there on the right-hand side, the CO2 tube, while the same equivalent R134 is a much, much larger tube. So the components for a CO2 system are much smaller than the R134A or other refrigerants. So it provides a higher cooling capacity and it has a more efficient heat transfer coefficient. That's the beauty of this system. So when I look at, from a cost point of view, what is the right size to bring in? If you look at this curve, 90% of the heating hours are less than 50% of the load, which implies if you want to be at 90%, you just need to have the heat pump to be 50% of the peak load, and you can use the existing boiler to provide the rest of the 50%. Or obviously you can always replace the whole 100% with a CO2 heat pump. But if you want to minimize your capital cost, this is a nice way to look at it. In other words, hey, just let's do half the system because it takes care of the 90% of the hours in the year. That's one way to look at it. The other way to look at it is, what is the total heating consumption load? And the 80% of the annual heating energy consumption actually occurs when the load is less than 25%. So if you want to be even more financially efficient, then you can say, hey, let me just do 25% of the load because 80% of the annual heating energy consumption happens in this 25%. So you can look at it either way. You can say I'll do only 25%, or you can say I can do 50%, or you can do 100%. But that's from a purely a business point of view. You can pick and choose what happens. That's that. Now, why we like CO2 is the steam COPs that we are shooting for are really in the range of 1.9. And if you do steam and chilled water, you're looking at 2.9 to 3.5. And when you look at hot water, it is in the range of 2.2 to 4.2. Actually, it would be much higher. It all depends on the temperature of the return hot water. If the return hot water temperatures are lower, then you're looking at a much higher than 4.2. And if you do, again, hot water with chilled water, your COPs are in the range of 3.5 to 5.5 or even greater depending on the temperatures of the water. So further than this, we are working to add an energy efficiency device. Energy efficiency device, which is really energy recovery on the CO2 side, because it takes the high pressure and the low pressure and puts the energy recovery device between the two of them. This increases the COP anywhere between to 15 to 25%. So this is in addition to what you see the numbers over there. So in summary on this CO2 heat pump, when we look at it, it has a high COP. It's very versatile. Ease of use because it's CO2, it's not any other nasty refrigerant, whether it is ozone depleting refrigerants or the newer ones, which are all PFAS, CO2 is much, much nicer, easy installation, and most important, low maintenance. The cost of the refrigerant is low, the maintenance cost is low, you don't need a registered technician, you don't need to collect your refrigerant. You have all of those benefits with CO2. Now I'll show you next is a slide that we just built. This is a demonstration system at our facility, the first of its kind. And that the picture on the left is the actual unit, R&D unit in our lab. And the picture on the right shows you steam coming out of the building. And that is 104 degrees C steam. And the condensate temperature, you can see it's fairly constant. So with this condensate temperature, we are able to produce steam at 104 degrees C consistently. So this is our demonstration product, which we will redesign and make it into a much nicer product when we do an installation in New York City sometime end of this year or early next year, which we are planning to do at a existing facility where we'll replace existing boiler with our CO2 steam-based heat pump steam generation system. So this is all about steam. The next thing I want to talk about is what I want to talk is addition of geothermal. But before I talk about geothermal, just want to put a comment here is that we can reduce the cost of electricity by shifting the electricity consumption from peak to off-peak hours by adding a thermal energy storage system. And we always like concrete. Concrete is a great, inexpensive thermal storage system. It can store heat, it can store cooling, whatever you want. And our CO2 pipes, which are very small, as you have seen previously, can go in and extract the heat or extract the cooling from the energy and reuse it at different time. Now, once we go from here, the next 3 slides, I just want to talk about the ground source heat pump, which is an addition to the heating and cooling system. A typical ground source heat pump is the picture that you see on the left-hand side, where you have a standard unit with a heat exchanger. And in this heat exchanger, you run a water loop which goes into the ground and comes back out. In the summer, the ground temperature is 57 degrees Fahrenheit, while the outside temperature could be anywhere all the way up to 100 degrees Fahrenheit in New York City or maybe more. And you can use this low temperature to cool the refrigerant, which increase the efficiency. The same thing, this is called the indirect exchange, the picture on the left. And the picture on the right is a direct exchange system. But here we are using CO2, where the CO2 goes into the ground and comes back out, goes into an expansion valve and goes to an evaporator and goes back to the compressor. Of course, this is the cooling PFD or PNID, and we can switch the valves and it will become a heating system. That's what a ground source heat exchange looks like. And quite a few times people ask us, hey, if we have an existing system, what can you do with CO2? Well, we can do, if you look at the picture on the left-hand side, where you have the water loop, we can replace this water loop with the CO2 loop and do an indirect exchange with CO2. Thar has filed a patent on this, and we like this for multiple reasons, especially because if you have an existing facility and you want to just convert that facility into a ground source heat pump, that's what we would do with CO2. Now, the real question is, why CO2? Well, the picture on the right, where you see the stainless steel tube, that's what we use to go into the ground. The diameter of this tube is 3/8 of an inch, which means the whole size that you have here is about 1.5 inches or 2 inches. If you look on the left-hand side, that's a standard 1.25 inch pipe, which has a 1.66 inch OD. You have to drill a 6-inch well to accommodate this. So what does that mean? That means that with CO2, you have less earth removed, less waste, lower disposal cost, less grout to put in, which drives the cost down, smaller piece of equipment compared to what you need for a 6-inch well, and lower mobilization cost. All of these things drives down the cost of drilling a geothermal well. If you look here on the bottom, this table, a drilling machine to do the 6-inch well, it could cost between $1.5 to $2 million, while it's only $300,000 for a 1.5 to 2.5 inch well. You can do 300 if you push it. You can do 500 feet per day with CO2. For the CO2 hole size, you can do 1,000 to 1,500 feet per day. And what this translates into, typically it costs $40 a foot complete for a conventional ground source heat pump well, while it costs a third, $10 to $15 for CO2. So our whole objective is drive down the cost of drilling, which is the main cost of ground source heat pump. And given the fact that we are losing all the grants for geothermal heating, we think that just our costs are so low that you don't need the grants to make it economic. So that's why we think a ground source heat pump in conjunction with a hot water unit or a steam unit is a great idea. Now, what you see here on the right-hand side in the picture at the bottom is that unit, which is really a small unit where you can drill. And the beauty of this unit is you can go to one place and drill vertically down or radially. So you don't need to make a lot of holes in your ground and run trenches to connect all of them. You just go to one place and drill, and all the pipes come to your place where you drill and you manifold them. So that again drives the cost of a system. So overall, we believe the ground source heat pump is a great addition to the existing heat pump system. Now here's a picture which we did this, as you can see, almost 12 years ago, March of 6, 2013, where ice melting, both on Mars, the picture on the left and the picture on the right, using the CO2 heat pump. And the picture in the middle gives you a photograph of the CO2 on the floor as it's running in the floor. Now, the most important slide really is this table that you see here. If you take a house and let's say you need 3 tons of heating or cooling, and the outside temperature is 25 C, typically 1 ton is 1 kilowatt. That adds up to be 3 kilowatts. Then as an engineer, you say, what happens if the weather outside is 45 C? You need something greater than 5 plus ton to provide the same 3 tons of heating. So the power consumption of your HVAC units go to 5 plus kilowatts. Now, if you look ground source, where the temperature is 15 C, then you really system, because the temperature is low, the CO2 is more efficient, you need a 2 kilowatt system. Then on the top of it, if you put an energy recovery device, your 2-ton system becomes a 1.7 kilowatt system. Then TAR is working on a new compressor technology which will further reduce that down to 1.3. So what you see here is you take a system, a traditional system which uses 5 plus kilowatts per ton for 5-ton system, and you can drive it down to 1.3 or even 1.7. That's a factor of 3 reduction. That has a huge savings, not only in the equipment cost of the HVAC unit, all the utilities, but also everything from the HVAC all the way down to the transformer, your electrical switches, your wiring, your connection, how big the transformer, especially if you have a multi-story building with lots of apartments. If you, let's say you had 100 apartments, you need 500 kilowatts for the HVAC compared to, let's say, even 170 kilowatts for the HVAC. Makes a huge difference in overall savings that you have by going to a ground source heat pump. So that's what THAR does, and I'm going to summarize our thing by saying we as a company, Clean Heat Technologies, can provide you a steam system, a hot water system, a hot air system, chilled water or even chilled air system, simultaneous heating and cooling, and finally we can integrate this into a ground source heat pump if needed, if we want to drive down the energy cost further. That's what we do. That's our company based on, and we have been doing this for a long time. As you can see from the slide, we started this work in 2012. Unfortunately, at the time, the Obama geothermal went away, so we dropped it out. But we are back into this picture, and thanks to NYSERDA through the Empire Technology Prize, we have been awarded one of the 7 finalists for it, and that's driving us to develop the steam-based heat pump, and we hope to have this demonstration soon. And with that, I'm going to stop. I think my time is up, and I'll be happy to take any questions, answer anything you guys would like to.
Great, thank you so much. One question has come in, and again, if anyone has questions, please post them in the chat and post them to everyone. One question that came in early in your presentation is, do you couple your system with thermal storage? I think you've covered that pretty significantly, but in addition to the geothermal that you mentioned, are there any other thermal batteries or things like that that you incorporate into your system or are compatible with?
So we like to like concrete and soil because the cost is very low. We do, the cost is very high. And if you switch between heating and cooling, then you need 2 different fluids. Let's say you want to do heat, then you need something that melts around 80 degrees Fahrenheit. And if you want chilling, you want something that melts around maybe 45 degrees Fahrenheit. So having 2 different fluids makes it very difficult. So you have to end up choosing one of them. So for that reason, we just decided we can use concrete where we can use heating or cooling on the same system. So that's what we like to use.
Great. Another question's come in. Can you please explain further how the heat pump would work along with existing boiler?
We are going to run the heat pump in parallel to the boiler. So let's say we size it for 50%, which is somewhere in the middle, and then 90% of the peak load is taken by the 50%, and the exit will supplement the rest when you need it. And the nice thing by keeping it that way, just in case you have to maintain the THAR's heat pump, you still have the boiler in place to take care of that while the heat pump is being serviced. So we like to run both of them in parallel, optimizing the cost by building only half the peak size that we need, and that gives you the substantial savings and carbon footprint savings by just running only half the heat pump, half of the peak load.
Great. Another question regarding building types. Can you say something about the types of buildings and the use cases that your system is optimized for? And for the demonstration project that you're working on, what type of building will that be?
So for the demonstration project, we are working with Fairstead to do in one of their buildings. They haven't picked the building yet, but it's something which is a 7-story building. As far as our technology is concerned, we are, it doesn't matter what kind of building you have, it's a very versatile system. It can work with any kind of building, and the demand, because we run a VFD, we can run the demand load, a large variation on the demand load because we are running a reciprocating pump, not a rotary pump, which gives us a tremendous range, anywhere between all the way down to 10% of the load to 100% of the load. That makes it very, very versatile.
Great. Thank you, Lalit. One last question. Can it work with high-rise buildings that need high-temperature steam?
Yes. We have a project with the Department of Energy where we will be producing 205 degrees centigrade steam. high pressure steam. So we will be using the same equipment that we are developing for NYSERDA and adding another piece to it, and that will drive up both the temperature and the pressure of the system to run at a much higher pressure and a much higher temperature.
Great, thank you. A request came in to share the slide deck. I would say if you want these materials from Lalit, you can reach out to him at the information provided here. You can also check out the recording of this session on the EBC Showcase Series website. So I want to thank everyone for attending today. Lalit, I very much want to thank you for delivering this valuable information. And we hope our audience can join us for the remainder of sessions that we have coming up.